So in a previous video I showed you how to build this 1.4 kilowatt induction heater, and then to power it in a separate video I built this 3 kilowatt power supply. And you see, that's a bit of a problem for me because now I've got a power supply that can output more than twice the power my induction heater can consume. So there's only one thing for it. No mucking around. We're building a bigger induction heater, and I'm going to show you how to do it in this video. Compared to my previous design, the capacitor voltage rating is now 600 volts AC, which allows for higher input voltages of up to 65 volts DC. To cope with the higher power demands, the design now features quad MOSFETs, allowing for up to 50 amps of input current. Compared to my previous design, the power rating has gone up from 1.4 kilowatts to over 3 kilowatts, more than enough to turn metal red hot for forging. Here we have the rare and elusive mechatronic Neanderthal. To attract a mate, this young single male must construct a functioning circuit. Unfortunately for this young male, he isn't using a custom printed circuit board, so there is only one way this can end. Oh dear. Thankfully this won't happen to you, because you can order a custom printed circuit board from JLC PCB. Starting from as little as $2 for 5 PCBs, they have fast production time and offer a wide range of design options and colours to choose from. So why don't you try out JLC PCB for your next project? Information about the components, PCB Gerber files, a schematic and extra info related to this build can be found on my website by using the link in the video's description. Before assembling the PCB, my first job was to wind a pair of inductors. These inductor rings are pretty cheap and easy to buy online. Next, I measured out a length of 16 AWG magnet wire to wind my inductors with. Since the current passing through the inductors would exceed the current rating of a single strand of 16 gauge wire, I'll use 2 strands, which should be more than adequate. Alternatively, you could use a single strand of 12 AWG magnet wire. When winding, try to keep the wire tight to the inductor ring. Large air gaps between the wire and ring will harm performance. And lastly, I remove the insulation from the wire using sandpaper, and that's the inductors done. I applied thermal paste to the MOSFET, and using a screwdriver to pry open the clip, I installed the MOSFET into the heatsink. With that done, I could focus on installing the remaining components onto the PCB. You should leave the capacitor, MOSFET and inductor leads long for the moment. The leads can be trimmed later. For the MOSFETs, don't forget to solder the leads on both sides of the PCB. Now there is going to be hundreds of amps of current passing through the capacitors into the work coil, and the thin copper traces on the back of the PCB are just not going to cope with those kinds of current. So we need to reinforce them. Now ideally I would say go and buy yourself a sheet of copper like I have here and cut out some bus bars to reinforce the traces. Now the only problem with me recommending this method is I'm assuming you have the tools and knowledge to cut out bus bars, because working with copper is actually kind of a pain. So to make it more accessible to a wider audience, I wanted to come up with an alternative method than just using copper sheet and cutting out bus bars. So let's see what I come up with. My idea was to use copper wire to reinforce the PCB traces for the high current they'll be carrying. So I grabbed a roll of 14 AWG electrical cable. This stuff is readily available and it's cheap. I stripped the insulation off 2 wires and crimped the lug on the end. Tinning the wires to the PCB is going to use a lot of solder, so do yourself a favour and buy a roll of thick solder. It makes the job so much easier. You will need a decent soldering iron to tin the traces and wire together. I'm using a TS80P iron, and to be honest it's underpowered for this job. If there are any capacitor or MOSFET leads still protruding, now you can trim them flush. To clean the flux from the PCB, I used lacquer thinners with a small brush. After tinning the cables to the PCB, I noticed the board had warped slightly. This isn't a big issue, but I do wonder if mounting the PCB to some sort of frame would have prevented the board from warping. Anyway, with the circuit board done, I moved on to making the work coil. First off, I cut out 16mm wide strips from a sheet of copper. The work coil will be made from 3/8 inch copper tubing. To connect the tubing to the PCB, I'll bend the strips of copper into a saddle that wraps around the tubing and solder them in place. I 3D printed this coil form tool. This makes it much easier to make the work coil. The tool not only produces a uniform coil, but it also prevents the tube from crushing. Alternatively, you can fill the copper tube with sand, plug the ends, to stop the tube from crushing while you're making the coil. The two short tabs will be used to support the weight of the work coil. Now I have to solder two more tabs to connect the work coil to the PCB. I used a spare PCB to hold the tabs in the correct position while I solder them onto the work coil. Now I could mount the work coil to the PCB using M6 bolts. I connected it to my power supply, which I built in a previous video. If you haven't seen it, then you can click the link in the top right corner. For now, I'll use 41 volts DC to power the heater. Later I'll be cranking up the voltage. At idle, the heater is consuming around about 230 watts. When I insert a piece of metal into the work coil, you can see the current jumps up, and this confirms the induction heater is heating the metal. Before I turn up the voltage, let's connect my scope across the work coil and take a look at the waveform. Well, it is a sine wave, however the bottom half of the wave isn't smooth. I have had this issue when I was designing my last induction heater, and it was due to ringing on the gate pin of the MOSFET. However, this time it's caused by the inductors operating beyond their saturation point. Later in the video I'll fix this issue, but for now let's power up the induction heater. The work coil is going to get very hot during prolonged use, so I connected the work coil to a water supply using PVC tubing. For now, the hot water exiting the work coil will just go down the drain. However, in the future, I'd like to have the work coil connected to a closed-loop radiator fan pump combo. I'll be using my extractor fan to blow air over the PCB components, and I'll be keeping a close eye on component temperatures using my temp gun. I placed a section of thick angle iron into the work coil, and the power consumption settles at around 1400 watts. I monitored temperatures over a few minutes, and the hottest components were the MOSFETs at 67C. With everything looking good, I could now turn up the power supply voltage to 50 volts DC, and watch the induction heater work its magic on this piece of steel. So I've hit a bit of a roadblock with my design here. At about 42 volts input, the inductors maintain a temperature around 60 or 70 C, which is fine, but they are at saturation point. And what that means is when I ramped up to 50 volts and above input, the amount of current going through these inductors has gone way past saturation, and these inductors are getting hot, up to around 120 degrees C when I pulled the plug, which is no good. Now you might be thinking, well gee, just go buy some bigger inductors. And that's a bit of a problem because they're very expensive. I have found some off-the-shelf inductors, but they are ridiculously expensive for this project. The other thing you might be wondering is why don't I just buy bigger toroid rings to make my inductors from? And yes, that is a viable option, but again, when I do find larger toroid rings, they are also very expensive and they're not actually easy to find. So there is one other possibility. If I stick with these toroid rings, which are relatively easy and cheap to buy online, why don't I just put two of them together? In theory, there's no problem in doing this, so let's give it a go. First off, I had to remove the inductors from the PCB. I use zip ties to temporarily hold the rings together. I measured out 1.6 meters of 2mm magnet wire to wind each inductor. In total, each inductor has 16 turns around the core, yielding around 60 microhenries of inductance. Doubling up the cores and almost doubling the inductance over the previous inductors should help smooth out the sine wave across the work coil. With the new inductors installed and ready to go, let's take a quick look at the waveform across the work coil using my scope. And that's looking much better. We've got a nice smooth sine wave. So with that issue solved, I think it's time to start melting some metal. I placed two fans over the PCB to keep the temps at acceptable levels. I I placed a thick piece of metal inside the work coil and watched it slowly turn red hot. As the metal heats up, the current will drop over time. This is because the internal resistance of the metal decreases with heat. Eventually the system will reach an equilibrium point where the metal won't get any hotter. Lastly, I want to briefly mention work coil design. As a starting point, I'd recommend making a coil with around 6 turns. To maximize productivity, you should design your work coil to closely fit the diameter of the metal you're intending to heat. In other words, if you're trying to heat a small metal pipe, you don't want a large work coil like I have here. I designed this work coil to closely fit this graphite crucible for use in a future project. Work coil design is a big topic in itself, and I'm still learning. You may have noticed on my new design, one of the coil connections has been moved to the back of the capacitor bank. Doing this helps to distribute the current evenly between all the capacitors. So my future plans for this induction heater, now it's built, I want to build an enclosure around it. Within the enclosure I'd like to add a radiator pump fan combo. The fan will blow cold air over all the components on the circuit board, and it'll also blow air through the radiator because, as I mentioned earlier in the video, I'd like to have a closed loop water cooling system for the coil here. It just makes it so much more portable and user friendly rather than always relying on having a water source close by to cool the coil. So that's my plans in the future. It's probably going to take a while to pull those off. But if you want to see it, don't forget to smash that subscribe button. If you want to know more information about the components and everything, then don't forget to check out the links in the video's description. Thank you very much for watching. If you found the video useful, smash that like button, it helps me out massively, and I will see everyone in the next video. Oh, can't forget my Patreon supporters as well. Thank you for your continued support, guys. Alright, I'll see you in the next video. Bye for now.